All right, good afternoon guys. Let's get started. So last time we started talking about functions and we defined a bunch of function terms. So in particular, what a function was, domain, codomain, range, image, preimage. And we also looked at the properties of being injective, surjective, and bijective. What I'm going to start talking about today is the idea of the inverse of a function. And this is something that was already kind of implied by what we were talking about last time when we were talking about being surjective. Although not quite. Not quite. So when we talked last time about being surjective, and we said one way to prove that is to find the preimage that gives you any particular image. Some people commented that that was kind of like finding the inverse of a function. And it almost is, except inverses aren't quite defined that way. The inverse actually requires you to be injective and surjective. So that's a subtle difference that we'll get into later. The inverse of a function is the function that undoes what the original function did, if that's how you want to think of it. And that only makes sense if the function is a bijection, if it's bijective. So if a function, let's say f, is bijective, then it's invertible. Which means it has something that we'll call the inverse. The inverse is denoted by f to the minus 1, right? Which kind of makes sense because the inverse of a number is 1 over the number. So the inverse of a function is f to the minus 1, if you like. And the way it works is it assigns to each element in the old B set, so the old domain set, the codomain set, a unique element in the old domain such that f of a equals b. All right? So the inverse is denoted f inverse, f to the minus 1, I'll read as f inverse. And it assigns to each b in B, so I'll say f here is a function from a to b. It assigns to each b in B the unique element a in A such that f of a equals b. So what this means is f inverse of b is a if and only if f of a equals b. That's how it's defined. And notice now it's hopefully clear why this function has to be both surjective and injective. Why does it have to be injective? Any ideas? Yeah?
So that, say, getting the inverse of b means that it will lead back to a single value of a.
Exactly. It leads back to a single value. Because if it weren't injective, it could lead to two values, and that would be bad. Right? It'd be bad because we wouldn't have a function. So for functions that aren't bijections, there's no such thing as an inverse. It doesn't exist. So inverses are not defined for functions that are not bijections. All right. So let's formalize why. One reason is if f was not injective, then that means some b has two preimages, and therefore f inverse of b would have two values, and that would mean it's not a function. right? One input can only give you one output. You can't ask a function a question and get two answers. On the other hand, if f was not surjective, then some b has no preimage. And this is a problem because f inverse of b would have no value. And if it has no value, then it's not a function. Right? The function should always give you an answer. Yeah?
Well, won't it then be defined for only the ones that do it?
Yeah, so you can define something like the inverse that gets around this limitation. The problem is if the function is somehow really not surjective, if you can sort of accept that informality, then the inverse, or this version of it, might not be of much use. But yeah, you can certainly define that. That's fine. Yeah?
So if a function doesn't have a value for some x, then wouldn't the square root of x not be a function, since square root of -1 isn't a real number?
Right, but remember, we're taking it from some particular set to some other set. So the fact that you can't plug that in means either, yes, as you said, it's not a function, or you gave it the wrong domain. So maybe the domain should only be the positive integers. Or non-negative, I guess. Other questions? All right. So the inverse can be found just like we did with those surjective examples, except now we also require it to be injective, otherwise it's not a function. Or the result won't be a function. So if you think about this in terms of the function diagrams we did, you can find the inverse by reversing the arrows. Right, that's the most natural way. The other way would be isolating the other variable in the formula. Right, so if your function is f of x equals 3x plus 2, for example, well, then let's say the output is y. So y equals 3x plus 2. You've isolated for y in the function, so in the inverse you would isolate for x. And that would give you the inverse of the function. All right. One important thing to note is that if f goes from a to b, then f inverse goes from b to a. Right, that's the point of what we're doing. Okay, so that's great. Let's do some examples of these things. So consider the following function. We have on the left a, b, and c, and on the right we have 1, 2, and 3. A goes to 2, b goes to 3, c goes to 1. Notice that this thing really is a bijection, so it makes sense to talk about the inverse. If we want to do the inverse, well then we reverse the directions of the arrows. So 1 goes to C, 3 goes to B, and 2 goes to A. All right, so if we say the original ones, f of A equals 2, f of B equals 3, f of C equals 1, then the inverse, f inverse of, let's say, 1, follow the arrow back to C, f inverse of 2, follow the arrow back to A, and f inverse of 3, follow the arrow back to B. Any questions about how I did that? This is okay? All right. So, moving on, let's see what happens if we have a formula instead. So let's say f goes from the reals to the reals, and it's defined by f of x equals 3x plus 2. So the example I was just talking about. We already know that it's bijective. We did an example like this last time. You can check your notes if you don't remember. So we know that it's bijective. So all we need to do is find its inverse. We don't have to check to make sure that it's defined first. So suppose that 3x plus 2 equals y. All we have to do is solve for y. So 3x plus 2 is equal to y, if and only if 3x equals y minus 2, if and only if x equals y minus 2 over 3. Okay? Therefore, f inverse of, I guess here it's y, equals y minus 2 over 3. If you wanted to say f inverse of x equals x minus 2 over 3, that's perfectly fine. Right? You don't need to change the letter. The only thing that's important is that this matches with that. That's all that matters. You can use any letter you want. I like to always keep it as an x, but some people find that confusing. You can do whatever you want as long as you're consistent. Any questions about this one? Yep.
Usually that doesn't make a difference because in the first example we had to like change which domain we were sampling from. So is it like x from like one set and y from the other?
Yeah, so in that case you have to be careful. But remember, in this case I'm going from the reals to the reals. So the inverse is also the reals to the reals. Yeah. Okay, so one more example. If I said from the integers to the integers, I have that fx equals x squared. What's the inverse of that going to be? Yeah? No inverse, why not? It's not bijective because it's not injective and not surjective, although if it were missing just one of those, it wouldn't be. Right? So this is not invertible because it's not bijective. And if I asked you this on a test or an assignment, I would expect more detail here. I would expect you to tell me exactly why it's not bijective. So you would do a proof that shows that it's not invertible, or sorry, it's not injective or it's not surjective. Right? But we did that last time, so I'm not going to do it again now. Other questions? All right, so the next thing I want to talk about is another thing about functions, another thing you can do with them, and that's the composition of functions. And if you're wondering how to do the last question on the assignment, it's this way. All right, so composition of functions. So you can do things with two functions just like you can do things with two sets. Right? If you have two sets, you can union them together or take the intersection of them and so on. Turns out that that's not so interesting with functions. What we do instead with functions is, well, you can add them together if you want, where if you have two functions f and g, f plus g of x is f of x plus g of x, if you like. But again, that's not too interesting. What's more interesting is the idea of composing functions. So that's taking a value, applying one function to that value, and then taking the result and putting it into another function. That's the composition of functions, and that's a little bit more interesting. So given two functions, let's say f and g, we can use the output of one as the input to the other. And when you do this, you get another function, right? It's making two steps, it's doing two steps, but you could describe it as a single function usually, and I'll show you how. So to create a new function, and the function looks like this. It looks like f of g of x. First you do g, get an answer, and then you put that answer into f, and then you get your final answer. There's shorthand notation for this, but I'll get to that in a second. what's going on here is first you evaluate G with input X. Then you evaluate F with the answer from 1, from the previous step. So it's a two-step process. All right? So if we say that F goes from B to C, and G goes from A to B, the composition of F and G is denoted F, and then a little circle, and then G. So it looks kind of like fog, but that's not an O, it's a very small circle. Okay? And you read this as F follows G. It's really important that you understand that that's how you read it, because if you remember that that's how you read it, you'll always remember the order that you evaluated it. It's F of G of X. Step 1 is evaluate G. G comes first. You have to do G first because that's what you feed into F. And if you look at the name, F follows G. Well, F follows G means F comes after G, which means you do G first. That's important to understand. It's very easy to get these mixed up, and it turns out that in general it's not the same if you get them mixed up. So F follows G is usually not the same as G follows F. One of your assignment questions is to tell me when it is the same. All right, so it's defined in the following way. F follows G of X is equal to F of G of X. Okay? And note, it's really important that we have G going from A to B and F going from B to C. So for F follows G to be defined, the range of G has to be a subset of the domain of F. Otherwise, it's not going to work. So let me just write that. Note, for F follows G to be defined, the range of G must be a subset of the domain of F. So all that's saying is the answer you get back from G had better be compatible with the kind of input that F is expecting. That's all that's saying. Does the definition make sense? Any questions about that? So the next 15 minutes aren't going to make sense if you don't understand it. Yep.
So basically, if f of x was a function that had g of x at the bottom, like divided by g of x, you can't have g of x equal 0?
It's a similar kind of restriction, although that's a different division by 0 restriction. This is a restriction on the domain and the codomain. So even ignoring what the function does, you have to look at the set that it goes from to the set it goes to. All right, so let's look at this graphically. That might be helpful in terms of these function diagrams we've been doing. So we have this set A, and let's say there's some element in there called little a. All right, we have this other set B, and notice up here G goes from A to B. So if I apply G to A, I go over into this set and end up somewhere. I've applied G, and I end up with G of A. Actually, I'm going to put that underneath so I don't have to overwrite G of A. That's what the function G does. That's just like we were talking about last class. This isn't anything new. But we also have this set C over here. And F goes from B to C. So if we take this G of A thing we got and follow whatever the function F says into C, we will end up at F of G of A. Is that okay? So what I'm doing in 2 steps, when I take the composition, I do it in 1 step. I go right from here all the way to over there, and this is the function f follows g. And again, f follows g means f comes after, and in this diagram I'm doing f second. Does this make sense? All right, so let's see some examples. So let's say we have a function g that goes from a, b, c to a, b, c, and f which goes from a, b, c to 1, 2, 3. Okay? So it's defined in the following way. G of a equals b, g of b equals c, g of c equals a, f of a equals 3, f of b equals 2, and f of c equals 1. Okay? So now I say to myself, okay, well, I'd like to come up with the composition. So let's figure out what f follows g is. So before I can do that, I need to ask myself, does that question even make sense? Does it make sense to ask what f follows g is? And I go up here and I say, okay, for f follows g to be defined, the range of g must be a subset of the domain of f. So the range of g, which is a, b, c, this thing here has to be a subset of the domain of f, which is this thing here. So is ABC a subset of ABC? The answer is yes. So it makes sense to ask what the composition f follows g is. So I've determined that yes, there is indeed an answer to this question. Now I have to give it. Yep. Yeah, this is just the definition of the function. Yeah. All right, so I need to figure out 3 things. What is the input to this function going to be? Well, it's going to be whatever the input to g is. So f follows g is going to have an input from g. So I need to say what the result for a is, what the result for b is, and what the result for c is. Okay. So now I just plug in the definition. What is f of g of a? What is f of g of b? And what is f of g of c? Well, f of g of a is just f of g of a is b. G of b is f of g of b is c. And f of g of c, well, g of c is a. So now I look up, well, what is FB? It's 2. What is FC? It's 1. And what is FA? It's 3. So now I know what f follows g is. And I can write this out explicitly because it's a small function. All right, so then the other question you might ask yourself is, well, what's g follows f? So in this case, I look back up at my rules. For f follows g to be defined, the range of the second thing has to be a subset of the domain of the first thing. So the range of the second thing is that, and the domain of the first thing is that. So is 1, 2, 3 a subset of ABC? No. So it doesn't make sense to talk about it. We can't do this composition. If you forgot that rule and wanted to try anyway, well, you would do this. So g follows f. I do f first, so I need to get an input from f. So g follows f of a. Well, even that one will be enough. G follows f of a. That's g of f of a. F of a is 3, so this is g of 3. And what is g of 3? Doesn't make sense, right? G takes ABC to ABC, and I just gave it a letter. So this thing doesn't make any sense, so it's not a function. That's why we have these restrictions. If you don't have those restrictions, then you can't do this operation. Okay, so let's try to see what happens when we have some formulas instead. So let's say f goes from the integers to the integers, and g goes from the integers to the integers. And let's say that f of x equals 2x plus 3, and g of x equals 3x plus 2. So in this case, f follows g and g follows f are both going to be defined, right? Because all of the sets are the integers, so there's never any case where they would mismatch. So both are actually defined. So first I'll do f follows g. F follows g of x is just f of g of x. What is g of x? Well, g of x is 3x plus 2. And what is f of x? Well, it's 2 times the input, which is 3x plus 2, plus 3. So all it is a matter of substitution. That's all you have to do. And we can clean this up a little bit, right? This is 6x plus 7. Right? Because I distribute the 2 to get a 6x plus 4 plus 3 is 6x plus 7. All right, what about the other one? So g follows f of x. Well, that's just g of f of x. F of x, I know it's 2x plus 3. And g of x is 3 times its input plus 2. And now I expand this out. I get 6x plus 9 plus 2 is plus 11. And it's important to notice here that these are different functions. Now in this particular example, they're kind of close. In fact, they're only off by 4. But they're different. Doesn't matter how close they are. So note that in general, f follows g does not equal g follows f. Sometimes it does though, and that's the last question on your assignment. So I give you 2 types of functions, and I ask you, when are the compositions equal when taken in either order? Okay? One important thing happens when you compose a function with its inverse. This is an example. One important case happens when you compose a function with its inverse. Okay. So suppose we had fa equals b. Well, then we know that f inverse of b equals a. That's the definition of the inverse. All right, so let's say we wanted to compose these. So f inverse follows f of a. Well, that's f inverse of f of a. We know that f of a is b, so f inverse of b, and f inverse of b is a. So notice that the input and the output are exactly the same. And in fact, the same thing works if you do it in the other order. So f follows f inverse of b equals f of f inverse of b. F inverse of b is a, so that's just f of a, and f of a equals b. And again, the input and the output are exactly the same. So this tells you when you take the composition of a function with its inverse, then you get back whatever you put in, and you can do it in either order. The composition works in either order. Any questions? Yeah?
Can we use these as a check, or are there any other functions that we use as check?
There are other functions, so in which way? That give you the same output, or that you can compose in either order? You can definitely do those individually. I'm not 100% sure if there's any other functions like that. I'd have to look that up. I'm not sure.
So if we're if we think we have the inverse of a function, can we try it? Can we use this to try it?
So if it didn't have this property, then you definitely wouldn't have the inverse. If it did have this property, then I'm not 100% sure. I'm not sure if there's any exceptions. Definitely just one of those two properties isn't enough, though, because there are plenty of functions who, you give some input, you get the same output, and there's plenty of functions that you can compose in either order. I'm not sure about the union or the intersection of those two sets. Other questions? All right, so we're going to move on. The next thing I want to talk about is something that's fairly simple, and that's the idea of a graph of a function. And this is sort of a subtle point that barely needs to be mentioned, but I will. You can plot a function f from a to b by drawing all points a comma b where a is in a and b equals f of a. So I'll do some examples. Let's say I had f that goes from the integers to the integers, defined by f of x equals 2x plus 1. How would this function look if I graphed it? Yep. Okay, so when you say linear function, that makes me think of something that looks like this. Is that correct? Yeah?
Many dots on that line.
Right, it's not the entire line, because if it were the entire line, the function would be from the reals to the reals. But it's not, it's from the integers to the integers. So it's just the dots on this line that are the at integer values. So in fact, what it looks like is this. I have a dot there, 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 and so on at every single integer. Okay? Here's another example. If I had f that goes from the integers to the integers, and I had f of x equals x squared, the exact same thing happens. I'm only doing the integers, so this is a parabola, but it's not completely filled in, because I only have integer inputs and integer outputs. If, on the other hand, I had f that goes from r to r, and f of x was x squared, well, then I would have the usual parabola shape. Then it would look like that. Are these distinctions clear? So for questions like this, the trick is it from the integers to the integers or from the reals to the reals? Yeah?
You put the arrows at the end of the real. Did you put the arrows at the end of the real?
I would if there was a nice way to draw that, but you can't really draw an arrow without a tail. So, I mean, I guess you could sort of draw it like that, but as soon as you draw a line, it makes it sound like all of those points are included. So yes, they do extend to infinity. I just don't have a nice way of drawing it. Other questions? All right, so we're ready to talk about the first thing that I think is neat in this course. Yeah. Okay, so that's the idea of countable and uncountable sets. So the problem with discrete math is you need a lot of tools before you can do anything neat, and we've just now got to the point where we can do something neat. When we were talking about sets, we talked about the sizes of sets, and I did mention that there's this thing that can happen where the set is infinitely large. We called it an infinite set, but I didn't really expand on that very much because it turns out that that's kind of confusing. The idea behind what we're about to do is to reason about sizes of sets that are infinitely large. And that's the idea behind what we'd like to do. And at first it seems like that's kind of laughable, right? We have two sets, they're both infinitely big, how can you compare them? Well, consider the following way of comparing the sizes of two sets. Let's say I gave you two sets, and I also gave you a bijection between those two sets. If I can do that, what do you know about the relative sizes of the two sets? Yeah?
It must be the same size.
Right. If I gave you a bijection between two sets, they absolutely have to be the same size. Right? If this set, let's say the set on the, so let's say I have a function f that goes from a to b. What happens if the set a is smaller than b? It can't be bijection because it can't be a surjection. Okay? What happens if the set on the right, the set B, is smaller than the set A? Then it can't be an injection. Okay? So if I can give you a bijection between two sets, then the sets have to be the same size. And interestingly, the converse of that is also true, right? If two sets are the same size, then there exists a bijection between them, for sure, right? Maybe not every function is a bijection, but there's at least one function that is a bijection. So, and conversely. And if you remember back to lecture 1, if you say and conversely, that's the same thing as saying if and only if, by the way. So notice that all of that, I never really talked about the set being finite or infinite. This logic applies equally well to sets of infinite size. So if we have two infinite sets and there's a bijection between them, then they have to be exactly the same size. That size is infinite, but they're the same size. Does that seem plausible? Okay, you say that now, but we'll see. All right, so consider one set. I'll call it Z plus. That's the set of positive integers. So it's 1, 2, 3, 4, and so on. Okay, that's Z plus. We call a set countable under two conditions. The first is if it's finite. So all finite sets are countable. Or there is a bijection between it and Z plus. And notice that that's exactly the same as saying it has the same cardinality as Z plus. And the reason we call it countable is because if you were looking at the elements of the set in order, you'd be able to say, oh, that's element number 1, that's element number 2, that's element number 3, that's element number 4, and so on. Okay, that's why we call it countable. And that idea brings up another way of thinking about it, and that is that you can list the elements in order. Right? Because if you can list the elements in some order, then the first thing is f of 1, the second thing is f of 2, the third thing is f of 3, the fourth thing is f of 4, and so on. Does everyone see how these three statements in number 2, it's clear how those are all equivalent? Yep.
I was wondering what cardinality was.
Cardinality is the size of a set, the number of elements in a set. Mm-hmm.
Is Z plus the same as natural number?
Yeah, but sometimes people get uppity about whether 0 is included, so Z plus completely disambiguates this. So some people differentiate between the natural numbers and the whole numbers, and I think people think that this is some universal agreed on thing by mathematicians, and no, it's just whoever's writing the textbook. I prefer z plus because the plus means positive and you know for sure that 0 isn't included. Another question? All right. So, if a set isn't countable, it's uncountable. Okay. So let's do some examples and see when and if our intuition of what these things mean starts to fall apart. So the very first question I'll ask you is, are there more positive integers or odd positive integers? So that's our question. In the back? Listed in order. So first, second, third, and so on. Yeah.
If it has the same cardinality as that plus, that means it's right?
So there's this sort of distinction here, right? They're both infinite sets, but do they have the same size? This is the question. They have the same size if there's a bijection between them. So we'll see examples of both. We'll see examples of infinite sets that have bijections between them and don't have bijections between them. That seems weird until you've seen some examples. And even after, it seems kind of weird. Yeah?
So there should be more positive integers because the odd positive integers is a subset and not the subset that is the same place.
Right, so in fact, the odd positive integers are a proper subset of the positive integers. So it seems that there would be more positive integers. Yeah? So in fact, you could do this logic with z minus because there's a bijection between z minus and z plus. So it's enough to find the bijection between z minus, but that doesn't so much matter here. So let's see what happens if we try to find a bijection. Let's try to find a bijection. Let's look at the function f, and it goes from, say, I don't know, and let's say z plus to z, oops, I'll call it O for the set of odd positive integers. All right? Okay, so I claim I wanted to find the function f of n equals 2n minus 1. So that's a perfectly good function. Notice that I can give it any integer I want, and it always gives me back an odd integer because it's 1 less than a multiple of 2. So everyone agrees that this function goes from z plus to O? Okay. So is this thing injective? Okay, well, suppose that f of n equals f of m. Well, then 2n minus 1 equals 2m minus 1. So 2n equals 2m. So n equals m. So it is injective. All right, let's check to see if it's surjective. Is this thing surjective? Any thoughts on that? This is kind of a tricky one to prove that it's surjective, right? Because we're going from O instead of sort of a normal one. Any thoughts? So can I get any odd number I like out of this? Yeah, in fact you can. So suppose we want image T, and it's in O, so that's the same thing as 1, 3, 5, 7, 9, and so on, right? Okay, well, what that means is that T is equal to 2k minus 1. Right? I mean, that's the form of all of these things. The very first one is 1. The very next one is 3. The next one is 5, and so on. Is that okay? So if you want, say, 1, you put in some value. If you want 3, you put in some value, right? The value you put in for 1 is 1. And then you'd have 2 times 1 minus 1 is 1. If the value you wanted was 3, you would put in 2. And then you'd have 2 times 2 is 4, minus 1 is 3. If the value you wanted was 5, you would put in 3. And then you'd have 2 times 3 is 6, minus 1 is 5. Okay? Therefore, yes, it is also surjective. This is exactly like what we did last class, except I have to be a little bit more careful here because I'm not drawing it from the set of integers, I'm drawing it from the set of positive odd integers. Okay? So that means F is injective and surjective, which means it's bijective. And since I found a bijection between the positive integers and the positive odd integers, that means they have exactly the same size. There are equally many positive odd integers as there are positive integers. Yeah?
But like, well, because they're both infinite, they're the same size, but
well, that's not necessarily true. We'll see that soon. They are both infinite, and they happen to both have the same size. Those are not the same statement, as we'll see soon. Yeah, you can have 2 infinite sets that do not have the same size. That's possible. Yeah.
Okay, so if this function is bijective, then it must have an inverse.
Yep.
How would you have a function that goes from instead of all positive odd integers to instead of all positive integers and to the number of every one?
Yeah, so if you look at the graph for this function, this is basically a line with slope 2, right? So,
Well, okay, let's dots, right?
sure, yeah, but it's the shape of a line with slope 2, so you'd be looking at the shape of a line with slope 1/2, basically. A little fudging for the y-intercept, but basically you have a line with slope 1/2. And that's what's really allowing you to do this, right? It doesn't have to be a line with slope 1. You can have any slope you like. Yeah?
Can you explain how the same size, even though one has substantially more elements?
Right, so the key observation here is just because one is a proper subset of the other does not mean that they're not the same size. Intuitively, it seems like they should. It should mean that. And if the sets are finite, then you do have that. But that's not the case for infinite sets. If you have infinite sets, just because one is a subset of the other does not mean anything about their relative sizes. And that's very counterintuitive. I agree completely that's surprising. But we all agreed a few moments ago that if I could find a bijection between the two sets, then they must have the same size. And I lived up to my part of the bargain, so now you have to believe me that they have the same size. Right? That was the deal. All right. So as if that weren't enough, are there more positive integers or rational numbers? I'll say positive rational numbers. So are there more positive integers or positive rational numbers? So again, the integers are a proper subset of the rational numbers. They're both infinite sets. Yeah?
this one, they're not the same size because for positive rational numbers, in between two positive integers, there's an infinite amount of rational numbers.
Okay. All right. Is that enough to do it, though? That seems promising. Let's see what happens. So what we need, so let's pretend that we want to prove that these sets are the same size. We need some function f that goes from the positive integers to the positive rationals. That's what we're looking for. And if you think back, remember that a bijection between the positive integers and some set is exactly the same as listing the elements of the other set in some order. Right? If I could list the elements of Q plus in some specific order, such that, you know, if you gave me a number, I can tell you which place it's in, then that's exactly the same as giving a bijection, right? Because if I list them like 1/2, 1/3, 1/4, 1/5, 1/6, and so on, that's not the order I'll use, but if I did do it that way, then I would be able to tell you, okay, well, the first thing on the list is 1/2, the second thing on the list is 1/3, and so on. So is it clear that that's okay? Does everyone accept that if I just list them in some order, that's the same as giving a bijection? Yes, okay, good. So, I just need to list, I shouldn't say I, that's kind of impersonal. We just need to list, even though I'll do it, the positive rational numbers in some way. And the reason is that is since the first element of that list can be F1, the second can be F2, and so on. So how do you achieve such a listing? All right, so a rational number has the form P over Q, right? We know that. And we know that Q is not 0. Right? All right. And since we know that we're dealing with positive rational numbers, I can assume that P and Q are bigger than or equal to 0. Right? One of them can't be negative. Right? That wouldn't make any sense because I'm only talking about the positive rational numbers. And if they're both negative, then really it's just a positive. Right? Because the negatives cancel and you get a positive rational number. So P and Q are both bigger than or equal to 0. So the way it's going to work is the list will consist of all positive rationals with P plus Q equals 2, then P plus Q equals 3, then P plus Q equals 4, and so on. That's the trick. That's how I'm going to list them. All right. And we also don't repeat any number if we encounter it again. Okay? And the key observation is there's only a finite number of rationals whose sum is some particular thing. Right? If I asked you to list all rational numbers a over b such that a over b is 5, how many are there? Or list them all. Right? It's 1 over 4, 2 over 3, 3 over 2, 4 over 1. Right? That's it. There's no more. Yeah? This is my construction. They don't have to. This is how I'm going to list them. So this is my idea behind the proof. And we'll see why that's useful in a second. So I'm going to list them this way. I'm going to do it in a grid. In the top left, I have 1 over 1. And to the right of that, I have 2 over 1, 3 over 1, 4 over 1, 5 over 1, 6 over 1, and so on. On the next row, I have 1 over 2, and then 2 over 2, 3 over 2, 4 over 2, 5 over 2, 6 over 2, and so on. And then I have 1 over 3, 2 over 3, 3 over 3, 4 over 3, 5 over 3, 6 over 3, and so on. And then 1 over 4, 2 over 4, 3 over 4, 4 over 4, 5 over 4, 6 over 4, and so on. 1 over 5, 1 over 6, 2 over 5, 2 over 6, 3 over 5, 3 over 6, 4 over 5, 4 over 6, 5 over 5, 5 over 6, and 6 over 5, 6 over 6. And all of these continue. So what I'm really doing is making a grid where the top number increases left to right and the bottom number increases top to bottom. So this isn't a listing yet because I haven't said which order to visit these numbers in. So does everyone agree that if I extended this grid out to infinity in every direction, every rational number would be on there? Every positive rational number would be on there. Everyone agrees with that? Okay. So what I'm going to do is I'm going to list them in an order, and the order is going to be this. I'm going to start here, and then I'm going to go to 1/2, and then I'm going to go to 2 over 1, and then I'm going to go to 3 over 1, and then 2 over 2, and then 1 over 3, and then 1 over 4, 2 over 3, 3 over 2, 4 over 1, 5 over 1, 4 over 2, 3 over 3, 2 over 4, 1 over 5, and continue like this. And that continues in that pattern. I need to do a little bit more work because right now I'm putting some numbers multiple times in my list, so I need to get rid of some of them. So for example, I've already output 1, so I don't output 2 over 2, 3 over 3, I won't output 4 over 4, 5 over 5, 6 over 6. I've already outputted 1/2, so I won't output 2 over 4, which is down here. I've already outputted 1/3, so I won't output 2 over 6, which is here, and so on. So I have to cross a bunch of things off. I haven't done all of them here yet, but that's the idea. And my claim is that this is a valid listing of all the numbers. Because notice what I'm doing here is in this angle, let me do it another color here. If I look at these sort of diagonal things, then this is P plus Q equals 2. This is P plus Q equals 3. This is P plus Q equals 4. P plus Q equals 5. P plus Q equals 6, and so on. And for each one of those, there's only finitely many rational numbers that have their numerator and denominator summed to that constant. Right? So there's only finitely many things in this diagonal, and in this diagonal, and in that diagonal, and in that diagonal, and so on. Everyone agrees with that? All right, so that means this is a listing of the rationals in order. In my order, but in order. So 1 over 1 is the first thing, then 1/2, then 2, then 3, then 1/3, then 1/4, then 2/3, then 3/2, then 4, then 5, then I skip 4 over 2 because I already did 2, and so on. But that's the order. So this thing here is an order. Does anyone not think that's an order? Yeah?
Can you explain why they add P plus Q adds up on the side?
Why they add up? So, I mean, that's the order I put them in.
So but like the third row, what do you add up to?
So the numerator is 1, the denominator is 3, so that's 4. Numerator 2, denominator 2 is 4. Numerator 3, denominator 1 is 4. So if I actually wrote down an expression for this function, it would be very ugly. That's why I'm doing it as a list instead, because I can describe what's going on without having to do some weird formula. So here's a question for you. If this is a valid ordering, why isn't it a valid ordering to do all of the first row, then all of the second row, then all of the third row, and so on? Why would that be bad? Yep. Sorry? I don't understand. Oh, it wouldn't end. Yeah, exactly. So the first row is infinitely long. So if someone asked you, hey, where's 1/2 in your list? You would say, oh, you go infinitely many things over, and then it's the next one. Right? That's not going to cut it. If someone asked me where 1/2 is in this list, I would say, oh, it's the second thing in the list. And that's no exception, right? If someone picked any one here, I would say, okay, well, what diagonal is that on, counting from the top left? And in doing that, I would add up a finite number of finite numbers, right? There's finitely many things in this first diagonal, finitely many in the second, third, fourth, fifth, and so on, until I get to the diagonal I'm interested in, and then I count how high up in that diagonal I am. So no matter what number you give me, I can give you a finite index that says that's where you'll see it. Whereas if I did row by row, I couldn't do that, because I would be saying go infinitely many over, it's the next one. Right? That doesn't make sense. So that's why this is a valid list. And this trick of saying, look at the sizes of P and Q, adding up to something, like restrict the sum of two things, that's very common for this kind of thing. That's a trick you'll probably see later, maybe. So all this to say, there are exactly many positive rational numbers as there are positive integers. Both infinite, but those two infinite sets have exactly the same size. And again, this is surprising because as you said, there's infinitely many rationals between two integers. It's true, but it doesn't matter. They're still exactly the same size. All right, so let's move on to another example. Are there more positive integers or real numbers? So this is the same thing as asking if a set of real numbers is countable, by the way. Let's actually, this is too hard. Let's make it even easier. So, are there more positive integers or real numbers between 0 and 1? So strictly between 0 and 1. Right? So if there are more real numbers between 0 and 1 than there are positive integers, then there's certainly more real numbers than there are positive integers. All right, so let's try to do that. Any thoughts before we embark on this? Yeah?
Yeah, you said if there's more numbers between 0 and 1, there's definitely more in general.
Yes.
But we just proved last time that even though, like that just seems really hard to be.
No, that's the opposite of that though, right? That's saying if this smaller set is bigger, then the bigger set is bigger. That's the opposite of saying if the smaller set is smaller, then the bigger set is not smaller or whatever. So it's not exactly the same logic, and that's why it works here. All right. So do we think these are the same size or no? Yes. Okay. So I mean, I had to stop sometime. So let's try to show that they're not countable and see what happens. Because so far, all the proofs we've done have been to show that they are countable. So let's see what happens if we show that it's not countable. So we will show that x such that x is a real number and 0 less than 1, less than x less than 1 is not countable. And the way you prove this, or one way you can prove this, is by contradiction. All right, so if we want to prove it by contradiction, we suppose that it is countable. And if it's countable, we can list the elements in order. Right? That's what it means to be countable. So I'm going to list them in this order, right? I'm assuming that it's countable, so I can do this listing. Yep.
Oh, you tend to go back to the first element. You can't find the first element.
So that is a bit of an issue, but that's not a rigorous proof that we can't. It might just be a proof that we don't know how. So instead, let's pretend that we can do it. It would look something like this. The first real number is 0 point, and I know it's 0 point because it's between 0 and 1. And then I look at all its digits. So D11, D12, D13, D14, and so on. I don't know what those digits are, but there's something. The next element in the list will be 0.D21, D22, D23, D24, and so on. The third element will be 0.D31, D32, D33, D34, and so on. And this continues, right? This will go on and on and on. Great. Notice that each Dij is just a digit, right? So it's in 0, 1, 2, all the way up to 9. Right? Each digit is 0 through 9 inclusive. That shouldn't be shocking. Great. And each one of these could be infinitely long, right? I mean, that can happen. There are infinitely repeating decimals. Is it possible for me to have 0.9 repeating in this list? No. Why is it not possible for me to have 0.9 repeating? Yep. Yeah, it's equivalent to 1. And I'm only talking about numbers that are less than 1. 0.9 repeating is exactly equal to 1. There's absolutely no difference between those two numbers.
Why is that?
Okay, because 0.3 repeating is 1/3, 0.6 repeating is 2/3, and 1/3 plus 2/3 is 1. That's the easiest proof I know. Okay, so that's just sort of an aside. It's an interesting fact that you can upset people with if they don't think about it too much. All right, so what we'd like to do is we say to ourselves, okay, we have this list. We have this list, and this list is supposed to have every real number on it. Every real number between 0 and 1. So if I could come up with a real number between 0 and 1 that wasn't on this list, that would be bad. Right? That would be a contradiction, because then my list would be bad, but I assumed it was good. That was the whole point of assuming that it was countable. So we're going to come up with a number, a real number, between 0 and 1 that is not on our list. And the number I'm going to do is, I'm going to call it R, and it's going to be 0.D1, D2, D3, D4, D5, and so on. And I haven't said what the D's are yet. Di is going to be equal to 4 if Dii is not 4, and it's going to be equal to 5 if Dii equals 4. And there's nothing special about 4 and 5 here. You can do any two different numbers that you want. So this is my number. All right, so let's think about what happens. What do I know about R and R1? So what's the first digit of R1? D11. And what's D1? Could it be the same? No. So if the first digit of R1 is 4, then the first digit of R is 5. And if the first digit of R1 is anything except 4, then the first digit of R is 4. So R definitely does not equal R1, since they differ in D1 and D11. They differ in the first digit after the decimal. Okay. R does not equal R2, because R2's second digit is D22. And if D22 is 4, then D2 is 5. And if D22 isn't 4, then D2 is 4. So R does not equal R2, since they differ in D2 and D22. And hopefully now you can see what's going to happen. R does not equal R3, since they differ in D3 and D33, and so on. So R isn't equal to the first thing. It's not equal to the second thing. It's not equal to the third thing, the fourth thing, the fifth thing, the sixth thing. Is it equal to anything on the list? No. It's not equal to the nth thing on the list because they differ in the nth place after the decimal. So if R is not equal to anything on the list, the only conclusion you can draw is that R is not on the list. And since R is not on the list, that means our assumption that we could make a list must be wrong. So we have a contradiction. And therefore, the real numbers are not countable. Okay? So to get back to the point you had made, a subset, if a set is uncountable, then a superset of that set is also uncountable. But the other direction doesn't hold. Okay? So there are strictly more real numbers than there are integers. Okay, the set of real numbers is actually bigger than the set of integers, even though they're both infinite sets. Okay? Even though they're both infinite sets, the reals are larger. Yeah?
Well, we didn't prove that they were bigger, we proved that they weren't the same size, they could be smaller.
No, they're not smaller because then I wouldn't have got a contradiction here. Maybe I'm not following. So you're saying we would, so that they're not the same size. So, right, they're not the same size, and they can't be smaller, because then you would have this containment relation. Yeah. Other questions about this? So this is pretty non-intuitive. One thing I would like you to think about, and this can be homework for you, although it won't be graded. Why doesn't this argument work for the previous examples? So it's kind of a subtle point, but a lot of people think that this argument would apply if you wanted to find a bijection between two sets that were clearly the same size, like Z plus and Z plus. Where does that fall apart? Why is that a problem? That's something I'll leave you guys to think about. That's it for today.